Hi guys, welcome to lecture 18, solving ordinary differential equations. Today we want to look at how to solve systems of first order differential equations. Now we're going to begin by introducing you to the very basic idea for solving systems of equations by converting them to higher order linear equations or nonlinear equations. And so this is a very important relationship between first order equations and higher order equations that allows us to interchange solution techniques between the two, depending on which one is more convenient at the time. So that's going to be the foundation for finding solutions to systems of equations. And then we'll look at how to visualize solutions to systems of equations. We'll look at an application to a mixture problem, and then we'll talk about a more general way of finding solutions to systems of equations without having to convert them into higher order linear and nonlinear equations. Now, this is the basic idea. There's a very important conversion principle, right? And let's just write down what a general system of equation looks like. Okay, so we have a system of first order equations. So let's say we have x1 prime, right, being some function, just a slope function, which depends on x1, x2, x3, and let's say it depends on n functions. Right? We have another slope function for x2, also depending on my n functions. And then I have another slope function for x3. Right? And then I have n slope functions that would allow me to determine my solution, which is a vector of x1 of t, x2 of t, xn of t. Right? So each of these solutions are just real valued functions, right? And so what I'm doing here is that I'm finding the set of real valued functions that satisfy the set of equations. Okay, and we are only at this point in time going to be focused on the cases where these are all just first order equations. All right. Now, of course, these slope functions can be linear or they can be non-linear. Okay. Again, the solution techniques that we are going to focus on are going to be for linear cases. Right. Okay. So we know how to deal with any single one of these equations. We've learned a whole bunch of techniques in the very first set of lectures on how to deal with first order equations. Right. And so how do we deal with a system of first order equations? Okay. And this is the basic idea. There is a conversion principle that allows us to go from a system of first order equations and convert these into higher order equations. So second order, third order, and so on and so forth. Okay. Now, this is very important because once we go from a system of equations into higher order equations, especially higher order linear equations, we have lots of techniques. In fact, we spend the bulk of this class discussing methods to solve higher order linear equations. So whether it's Laplace transforms for constant coefficients, piecewise continuous functions, or undetermined coefficients, or variation of parameters, or series solutions, we can handle higher order, linear equations. Right? And so this is going to be the go-to approach for solving systems of equations. When we can conveniently do this, we will convert them to higher order equations. Okay, and the beautiful thing is that it's not a one-way street. We can go back from higher order equations to systems of equations. All right, and so in the very last section of this lecture, we're going to discuss more general techniques for solving systems of equations that does not require the conversion to higher order equations. So in the case where you have a higher order equation that you cannot use conventional methods to solve, you can always attempt to convert it back to a system of equations and then use this general technique for system of equations to handle. Okay, and so really the choice is yours with this conversion approach, right? You being able to successfully go back and forth between these two worlds allows you to now use the methods that you find most convenient to solve whether it's a system of equations or higher order equations. Okay. And so what we're going to spend the next couple of examples doing is just to practice how we can go from a system of first order equations to higher order equations, and then how we can go from higher order equations to a system of first order equations. And then we'll actually discuss the solution technique. All right, so let's take a first example here. We have x prime prime is x cubed plus x prime all cubed. This is a second order nonlinear differential equations. Okay, now we are going to attempt to convert this to a system of first order differential equations. Right. And here's the idea. We use a substitution approach. Right. And what do we substitute? We substitute the derivatives, beginning with the first derivative. And we just give it a new name. Right. So for example, I can set x prime to be a new variable y. Right. If I do that, then x prime prime will be y prime, right? And that will be given by x cubed from my differential equation, x cubed, right? Plus, since x prime is y, I'm going to call this y cubed. Okay, and so now I have the system x prime equals y, and y prime equals x cubed plus y cubed. And voila, I have a system of first order nonlinear equations. Okay, and the solution to my system will be a vector of x and y. Okay. Right, let's take another example. Now we have a third order linear non-homogeneous differential equations. We want to convert this to a system of first order equations. So again, we're going to make substitutions for the derivatives beginning with the first derivative. We don't substitute the unknown function x, right? We are only going to start substituting its derivatives. Okay, so we're going to set x prime to be some new variable y, right? And then y prime will just be the second derivative of x. Now, because this is up to the third derivative, I'm going to define x prime prime as another new variable, z, so that z prime will just be the third derivative of x, and that will be given by, I can solve for the third derivative from the differential equation here. And so my third derivative will be sine of 2t right, plus 5x minus twice x prime, but x prime is y, then minus 3 times x prime prime, x prime prime is z. And so I have a system of equations. X prime is y, y prime is z, and z prime is sine 2t plus 5x minus 2y minus z. And this is my system of first order equations. Notice that my solution to this system is going to be a set of functions x, and x could be a function of any independent variable, and y and z will be functions of the same independent variable. Right? So let's say the x is a function of time, y is a function of time, and z as a function of time. This will be my solution to the system of equations. So I have 3 equations, 3 unknowns. Right. Now, notice that here, the third order equation is linear. And if you look at my system of equations, each of these equations is a linear equation. Right? I don't have to deal with any kind of powers or products of the unknown functions or their derivatives. Okay. Now, in the previous example where we had a nonlinear, differential equation to start with, second order equation, we ended up with a system of nonlinear equations. And this is usually going to be the trend, that if your higher order equation is nonlinear, we expect that the system of equations we get will be nonlinear. And then vice versa, if the higher order equations is a linear equation, then the system of equations will also be linear. Okay, now our focus in this section will be on dealing with linear equations. So going from higher order linear equations to systems of linear equations. Okay, so we can go from higher order to system. Now, what we actually want to look at is how to go from system to higher order, because we know how to deal with this. We can solve this equation using a method of characteristics. So we can use a characteristic equation to solve the homogeneous problem, use undetermined coefficients or variation of parameters to find the solution to the non-homogeneous problem, and then combine the two. Right? So we can deal with this. But this guy is a new guy on the block. Okay, we don't know how to deal with this. So let's see how we can go backwards. Because if we can go backwards, then at least we will have a solution technique to deal with this. Okay, so here we have a system of first order equations. Right? We want to convert this to higher order differential equations. Right? So how do we do this? Okay, we have x prime is minus 2y, and y prime is 1/2 x. Okay, now again we proceed by making a substitution. Right? But this time we introduce a derivative into one of these two equations. What I mean is, here we have x prime equals minus 2y. Okay, now I can choose to write my higher order equation either in terms of x or in terms of y. That should be your choice. Okay, but you can only have one unknown function in a higher order equation. You cannot have two. Right? And so if I decide that I want to convert this to a higher order equation in terms of x, then what I would do is to focus on the equation involving the derivative of x. Okay, and then I'm going to try and make a substitution for y to get rid of the y in this equation. Right? Now, since I have an equation for the derivative of y in terms of x, if I want to make a substitution for the y here, what I can do is to differentiate this equation once. That will introduce a y prime into the first equation. Let's call this equation 1, and let's call this equation 2. So if I differentiate the first equation, I get x prime prime is minus 2y prime. Now I have introduced a y prime. Then I can use my second equation to replace y prime. So I have x prime prime is now minus 2, 1/2 x. Right? And now I have an equation x prime prime plus x is equal to 0 solely in terms of x. This is a second order linear homogeneous equations. Right? And this we can solve very happily. Right? So once we can solve this equation using the methods that we've studied so far for x, once we get x, we can always come back and find y. How do we do that? Well, from the very first equation, if you know x, then we know that, so from equation 1, right, we know that y is minus 1/2 x prime. So once we find x from this first equation here, then we can just take the derivative of x, plug it here, and then we have y. And that gives us the solution to the system of equations x and y. Right. Now this is a very exciting technique because it allows us to use everything that we have studied up to this point. Nothing gets wasted. Right. We are directly applying methods for solving higher order linear differential equations and nonlinear equations that we've studied to solving systems of equations. So there's no new thing here. The only new thing is the ability to go between these two worlds of systems of equations and higher order equations. Okay. Now let's go ahead and completely solve this problem. Since we have now come up with a higher order, a second order equation in terms of x, we can safely deal with this. So our equation is now x prime prime plus x is 0. Right. So we can go ahead and assume that my x, let's say it's a function of t, is e to the rt. Right. In that case, our characteristic equation becomes r squared plus 1 equals 0. And so we have r is plus or minus I, which tells me that my x of t will be c1 cosine of t plus c2 sine of t. Okay. Now from my first equation, I have that y is minus 1/2 x prime. So since I have x now, I can find y by differentiating x. This is going to be minus c1 sine of t plus c2 cosine of t. And if we plug this in here, then y of t will be minus 1/2 minus c1 sine of t plus c2 cosine of t. That simplifies to minus c1 on 2 sine of t, sorry, plus c1 on 2. And then we have minus c2 on 2 cosine of t. And that is my solution. Right. So I have x of t being c1 cosine of t plus c2 sine of t, and I have y of t being c1 on 2 sine of t minus c2 on 2 cosine of t. So this is a fairly straightforward approach. Right? As long as you can remember how to solve higher order equations, you can always solve systems of equations. That's what we're saying. Now, of course, it gets to a point where doing this conversion might not be the best thing to do, and so we'll look at, for example, if we have a system of 10 equations, right? It may not be the best idea to convert it to a 10th order differential equation, because that might be a lot of work, right? And so, towards the end of this lecture, we'll look at alternative methods that can be applied to directly solve systems of equations. But if you have 2 equations, 3 equations, even 4 equations sometimes, you can conveniently convert them to higher order equations and then use, the characteristic equation to solve. Okay, but that will be left to your discretion on what exactly you want to do, unless I specifically say do this or do that. Okay. So we have 2 equations which define the solution to the system, right? X and Y. Now the question we want to look at next is, how do we visualize our solutions? Visualization. Right. So let's say that I define my t, to be within some interval a, b, and I want to look at the behavior of these 2 equations, x and y. How can I visualize them? Okay. All right. So there are a couple of things that you can do. The first and I guess most obvious thing you can do is that you can plot the 2 equations separately, but on the same graph. So let's say this is a t-axis, right? I can decide to first look at how my x of t looks like for some range of t values, right? And then I can superimpose that with y of t on the same axis, so that I can look at the relative behavior of the 2, if that is of interest to me, within a specified domain, AB. Okay, and here I can talk about, the nature of the solutions, right? How do they interact? So as x increases, maybe y is decreasing, or they are both decreasing, or when do they reach their maximum? When do they reach their minimum? All of these questions you can answer by looking at the 2 graphs superimposed on each other. Okay. Now, the problem with this superimposition is that you can only look at a short-term behavior of the 2 solutions. So you can only look at them over, a certain range of parameter values. You cannot get a sense of how they look like, say, for all time. Okay. And if you want to get a more long-term view of your solutions, you can use what is called a phase plane portrait, right? And this is nothing, crazy. All that it is you're going to do a plot of the curve that is defined by your solutions as parametric equations, right? So think about the curve that is defined by x of t and y of t as parametric equations. So I can put my x of t on the x and my y of t on the y, and I can think about, well, what is the curve that is defined by these 2 parametric equations? That curve can tell me a lot about the behavior of the 2 solutions for all time, right? Because all that this curve does, it tells me how the 2, so at each point, it's telling me a pair of values. It's telling me a value for x and a value for y. But it's telling me this for every possible time. Because as I move along this curve, my time is increasing, right? And so the behavior of the pair of solutions for all time is very easily visualized by this phase plane portrait. Okay, so for example, if my solutions happen to lie on a closed curve, right, then I can get the sense that there is some periodicity present. Means that after some time, my 2 functions repeat themselves. right? Which is the only reason why they will lie on a closed curve, is if they repeat themselves. And so just by looking at this phase plane portrait, you can talk about, if there's any periodic behavior. Right? Sometimes you can also get that, well, your phase plane portrait, demonstrates some kind of limiting behavior for your graph. So you could have that your curve, just approaches some limiting value. Right? So it goes round and around. It's like a spiral, right? And eventually it gets closer and closer and closer to some point. Okay, and so you can identify that, oh, it looks like my solutions converge to some limiting value. And that is important information to have. Okay, and you can do this with the phase plane portrait. So whereas the two graphs superimposed allows you to temporarily analyze the two solutions within some fixed domain of the parameter, right? The phase plane portrait allows you to look at them over an extended period of time and look at their combined behavior. Okay. Now, the final thing that you can do to visualize your solutions is just look at the direction field, right? And the direction field you can get by just looking directly at the differential equation. Right? So we have that x prime is minus 2y and y prime is 1/2 x. Okay. If I want to look at the direction field, remember that the direction field gives us the tangent line at each point, the slope of the tangent line at each point, right? And so my slope, which is dy dx, right, is the same as x prime at y prime, which is dy dt divided by x prime dt dx. Right? So this will be y prime, which is 1/2 x divided by minus 2y. So you have minus 1/4 x over y. And then at each point, you can plot 1 and minus 1/4 x over y, which is going to be your equation, your slope of your tangent line at each point, rise over run. Right? And so with this, you can visualize, the family of solutions. Okay. So both the superimposition and the parametric curves with the phase plane portrait are visualizing one particular solution, one particular pair of solutions, right? But the direction field, remember, it allows you to visualize the family of solutions. So now you're not looking specifically at some fixed constants, right? But you're looking at all possible solutions of your system. So that is also a different, it also has a different kind of value, because now you can look at how the entire family of solutions behaves, right? So that is really the attraction of the direction field. Okay, so all of these visualizations have different, they give us different sets of informations, and really it's up to you to decide which one you want to use at which point in time. It totally depends on the kind of information that you want to extract. Okay, now for this particular problem, I want to show you how some of these graphs look like. So let's switch over to Mathematica. Right. This is a code that I wrote in Mathematica, and here I'm showing you the two solutions, x of t and y of t superimposed. I picked some fixed values for x, and for the coefficients c1 and c2, right? And you can see that we can begin to look at how these two graphs are interacting. Okay, but this is only for a fixed time period, and this is only for a specific solution, x of t and y of t. Okay, this is how the phase plane portrait looks like. I'm using the parametric plot function, right? And now you can see here that, oh, well, my x of t and my y of t seem to be moving along an ellipse with some predefined major and minor axis. And because they lie on a closed curve, I know that x of t and y of t are periodic, right? And I can see from the superimposition that they are periodic, because I can see that, of course, they are sines and cosines, and so they are going to repeat themselves after a while, right? But this shows very clearly the periodic behavior, right? And this graph is telling me how they're going to behave for all time, because I just keep going round and round and round and round and round this ellipse. Okay, and this is how my direction field looks like. Okay, so notice that the direction field is just showing me that, oh, if I change my coefficients, then I'm just going round and round different sizes of ellipses. So the entire family of solutions is a family of ellipses that I'm traversing as I change my coefficients. I just change the ellipse that I lie on, right? And so this is very useful information that these three different visualization techniques can give you about the solution to a system of differential equations. Okay, let's go back to presentation. All right, so now we know how to solve at least a system of first order differential equations by converting them to higher order equations. And we know how to visualize these solutions, right? Now the next question is, what are some natural settings, or what are some application settings that we can get a system of equations to solve? Right? We know how we can get, for example, a second order linear equation. We know it comes from a spring mass system. We know how we can get first order equations. We know it comes from population growth or temperature, monitoring temperature or exponential decay, right? And so where do systems of first order equations come from? Next question. Right. So here's an application, and this application is a more advanced version of the mixture problem that we handled in the first chapter. Okay, in the first chapter we had a single tank, we had an inlet and an outlet, and we wanted to monitor the amount of salt in the tank at any time t. Okay, now we can extend that problem by introducing a second tank or even two extra tanks. Connect these tanks together, and then we can think about how the amount of salt changes in all, let's say, two tanks or three tanks over time. Whereas when these two tanks are actually exchanging material. Okay. Now it turns out that when you have two tanks, the equations that describe the amount of salt in each tank for over time is a system of two linear equations. If you have three tanks, you get a system of three linear equations. So you can imagine a very complicated arrangement of tanks giving you, an nth order system of differential equations. And you can attempt to find out what the concentration of, in this case, salt is in each tank over time. Okay. Now, this is a very useful concept that is applicable in mathematical biology, right? Because one of the things that is of interest in mathematical biology is to be able to monitor, for example, the oxygen levels in the lungs and the heart of a healthy individual versus an individual that has a disease. Okay, now you can think about, the oxygen level as the concentration of, or the amount of salt. Now we know that there are, arteries and veins that connect the heart to the lungs. And these arteries carry oxygen, the veins carry oxygen back. So there is an exchange of oxygen between the heart and the lungs, which is very similar to an exchange of salt between these two containers, right? And one could set up a system of equations that can help us to determine what the concentration of oxygen is in the heart and the lungs of a healthy individual per unit time by solving this system of equations. And then we can easily compare that to somebody who may have a cardiovascular disease or a lung infection, and then figure out what is really going wrong, and probably use the difference in solutions to diagnose, some defect in the functionality of the lungs or the heart. Right. Now, of course, the heart pumps oxygenated blood to every organ in the body. And so you can immediately see how this can be extended to a system of n equations by just throwing in the liver, the pancreas, and other vital organs, the kidney, and then monitoring the levels of oxygenated blood in each of these organs, right? And so this is a very useful concept that applies to a very wide range of fields. And we are only using the brine as just a prototype of what can actually be a much more interesting problem for us to solve in different fields of study. Okay, so let's see how we can set this up. And then we'll come up with a solution to this problem. Right? So consider two brine tanks connected, and I'm going to just switch over here to the whiteboard so that we can have more space to work. Right. So let's just take the most important details from this page, because we are not going to be coming back. Right? We have two brine tanks, and I'm going to show you how they are connected. There's 100 gallons of brine in the first tank, and there are 200 gallons of brine in the second tank. Right? The brines are connected to each other, and so they exchange brine between each other. Right? And brine is pumped from from each tank to the other at a rate of 10 gallons per minute from tank 1 to tank 2, and 30 gallons per minute from tank 1. From 10 gallons from tank 2 to tank 1, and 30 gallons from tank 1 to tank 2. Right? And then we also have fresh water flowing into tank 1 at a given rate, 20 gallons per minute, and we have brine flowing out of tank 2 at a rate of 20 gallons per minute. Okay. And then so our interest is to write down a system of equations that can allow us to monitor the amount of salt in each tank over time. Okay, so that's exactly what we're going to do. So first off, how are these tanks connected? So this is example 4. All right. We have a smaller tank. This is tank 1. Let me reduce the size of this because I need more space to run. Okay, so we have tank 1 here. And then we have tank 2. Much bigger tank. Right. Now tank 1 holds 100 gallons of brine. Tank 2 holds double that amount, 200 gallons of brine. Right. There is an exchange of brine between the two tanks. Right. Brine is pumped from tank 1 to tank 2 at a rate of 30 gallons per minute. And then brine is pumped from tank 2 to tank 1 at a rate of 10 gallons per minute. In addition, we have pure water that is being pumped into tank 1 at a rate of 20 gallons per minute. And then we have brine being pumped out of tank 2 at a rate of 20 gallons per minute. Okay, and we're going to let x of t denote the amount of brine in tank 1, and y of t denote the amount of brine in tank 2. And our task is to find out x of t and y of t. Okay. All right, so the first thing we'd like to do is to write down a system of equations that can tell us the amount of brine in tank 1 and the amount of brine in tank 2 at any point in time. Okay. And so, just like we did before, the change in the brine in tank 1 will be an inflow concentration. Let's denote this by inflow concentration of X times an inflow rate minus an outflow concentration times an outflow rate. Okay. And the same thing for Y. We have an inflow concentration times an inflow rate for tank 2 minus an outflow concentration times an outflow rate. Okay. So notice that there are two inflows, right? So two outlets at which brine is flowing into tank 1. Okay, so I have two inflow concentrations and two inflow rates. Right. So for the first one, there's pure water that is being pumped at a concentration of 0 pounds per gallon, right? Times, and it's coming at a rate of 20 gallons per minute. And then in addition, there's brine coming from tank 2, right? And that is coming at a concentration of the amount of salt in tank 2 divided by the volume of brine times the rate is 10 gallons per minute. Okay, so this is the total, concentration, total amount of, you can think of it as a total amount of salt that is coming into tank 1. Right. Now, what is the total amount of salt that is going out of tank 1? Okay. The only brine that is going out is from tank 1 to tank 2. All right. And that is going out at a rate of 30 gallons per minute. The concentration will be the amount of salt in tank 1 divided by the volume of salt, the volume of brine in tank 1. So this times 30 gallons per minute. And that's the only outflow channel. All right, now let's look at tank 2. Okay. Let's look at the total amount of salt that is coming into tank 2. Right. Okay. So there's brine coming from tank 1 to tank 2, right? That is coming at a rate of 30 gallons per minute with a concentration of the amount of salt in tank 1 divided by the volume of salt in tank 1. Okay. And that is the only source of brine coming into tank 2. Right. Now let's look at the brine going out of tank 2. Right. Okay, so there are two ways in which brine can leave tank 2. We can either leave tank 2 and go into tank 1, right? So brine is being pumped out of tank 2 into tank 1 at a rate of 10 gallons per minute. The concentration of that brine will just be the amount of salt in tank 2 divided by the volume of brine in tank 2 times 10 gallons per minute. Plus, there's also brine being pumped out of tank 2, right? That is going out at a rate of 20 gallons per minute with a concentration of the amount of salt in tank 2 divided by the volume of tank 2. Okay. So we have all the information that we need, and we can write down our differential equation. Now, the only thing that we have to think about is what is the volume of brine in the tanks at any point in time. Okay, so let's think about what is going on. We start off with 100 gallons, every minute we gain 20 gallons from the pure water, and then we gain 10 gallons from tank 2. So we gain 30 gallons, and then we lose 30 gallons every minute. And so the volume of brine in tank 1 is going to stay constant. It's going to stay at 100 gallons because we are losing as much as we are gaining. Okay. Then in tank 2, every minute we are losing 10 gallons to tank 1 and 20 gallons outside. So we are losing a total of 30 gallons, and then we are gaining a total of 30 gallons from tank 1. So we are losing as much brine as we are gaining, and so the volume of brine in tank 2 will also stay constant. So we can write down these equations. The x dt is going to be, we have 10y over 200 minus 30x over 100. And then in tank 2, for the inflow, we have 30x over 100 minus we have 30y over 200. And so if we simplify that, we come up with the equations. The x dt, let me use x prime. X prime is going to be 1 over 20y minus 3 over 10x. Y prime will be 3 over 10x minus 3 over 20y. And so we can solve this system of linear equations for x of t and y of t. And that will tell us the amount of salt in both tanks at any point in time. So this is the first part, is actually to set up the mathematical model, right? Based on the very general idea, that the change in the amount of salt is due to the total amount of salt that comes in minus the total amount of salt that goes out. Okay. And so now the next thing we want to do is to actually solve the system of equations using the idea of conversion to a higher order equation. All right, so let's do that. I'll just go into a new space. This is part B. And let me write out the equation again. X prime is y over 20 minus 3x over 10. Y prime is 3 over 10x minus 3 over 20y. Okay. Now I'm going to choose to write this into an equation involving just x. Right, so I'm going to convert this to a second order equation involving x, which means that I need to replace y in equation 1. So I'm going to start off by differentiating equation 1. This is y prime over 20 minus 3 over 10 x prime. Right? So I have x prime prime plus 3 over 10 x prime is y prime over 20. Right? And then I have an equation for y prime here. So I'm going to make that substitution. So I have here 1 over 20 times 3 over 10x minus 3 over 20y. If we simplify that, we have 3 over 200x minus 3 over 400y. I'm going to send this over to the left-hand side because I'm grouping all the x's. It's 3 over 10 x prime minus 3 over 200x is now minus 3 over 400y. Okay, so now we need to replace y. And where do we have y? Going back to equation 1, right? Notice that x prime plus 3 over 10x times 20 is precisely y. So if I make that final substitution, I have x prime prime plus 3 over 10x prime minus 3 over 200x. This is now minus 3 over 400y, which is x prime plus 3 over 10x times 20. Okay, so this gives me minus 3 over 20 x prime minus 9 over 200 x. So now I can move everything to the left-hand side, and I have x prime plus, I have 6 over 20, I'm sorry. I have 3 over 10 plus 3 over 20 x prime. I have 9 over 200x minus 3x over 200 equals to 0. And if we simplify that, we have x prime prime plus 9 over 20x prime plus 6x over 200 is equal to 0. If I multiply through by 200, I have 200x prime prime plus 90x prime plus 6x is equal to 0. And that is a second order linear homogeneous differential equation in terms of x, which I can solve, right? Because we have tons of experience dealing with this. So let's go ahead and solve that. $200 x prime prime plus 90 x prime plus 6x equal to 0. If we assume a solution of the form e to the RT, right, we can derive a characteristic equation. It's 200r squared plus 90r plus 6 equals to 0. If we use the quadratic formula, we come up with the fact that R1 is minus 9 over 40 plus 1 over 40 square root of 33, and R2 is minus 9 over 40 minus 1 over 40, the square root of 33. And so this gives us x of t. This is C1 e to the minus 9 plus square root of 33 over 40 times t plus C2 e minus 9 minus square root of 33 over 40 times t. Right. So that is my, that this gives me the amount of salt in tank 1 at any point in time. Okay. Now I also need to know the amount of salt in tank 2 at any point in time. Right. How do I get that? Well, remember that we have an equation for y in terms of x prime and x. All right, so going back to this equation, we only need x prime. Right? And so we can calculate x prime as being minus 9 plus root 33 over 40 times C1 e to the minus 9 plus root 33 over 40 times t plus C2 minus 9 minus root 33 over 40 times e to that very exponent. Right. And then if we substitute x prime and x back into my equation, I can find out that my y of t is 3 plus the square root of 33 over 2 C1 e to the minus 9 plus root of 33 plus 3 minus root 33 over 2 C2 and voila, this gives me my x of t and y of t. Okay, but notice here that these are just general solutions, right? Because I still have to determine what my C1 and C2 are in order to get a particular solution. Okay, but that's not hard to do. We just have to define initial conditions, right? So let's assume that the amount of salt initially in tank 1 is 4 pounds, and that the amount of salt initially in tank 2 is 2 pounds. Okay, if we apply these initial conditions, we're going to get that C1 is 2 root 33 minus 2 divided by root of 33, and C2 is 2 times 2 plus square root of 33 divided by the square root of 33. And so that defines a particular solution for the two. And then now that we have a particular solution, we can answer, any question that we want. We can answer, well, what is the amount of salt in both tanks, say after 30 minutes, right? You just have to find x of 30 and y of 30. Right? And that gives you the amount of salt in both tanks after 30 minutes. Okay, so I went ahead to superimpose the two solutions, x of t and y of t, on the same axis, just so that we could get a sense of how the concentrations are changing over time. So this is done in Mathematica, and this is what it looks like. If I plot both tank 1 and tank 2, so tank 1 is in blue, and tank 2 is in this light brown here. Right? So notice that tank 1 begins from 4 pounds, tank 2 begins from 2 pounds, and we can, just by looking at the graph, we can see the dynamics of the salt change in the two tanks over time. Right? Now notice that because we are pumping pure water into tank 1, its concentration declines much quickly over time than tank 2, because we keep diluting tank 1, right? And then we exchange material with tank 2. So it takes a while for tank 2 to actually see a decrease. What actually happens is that there's an initial increase in the amount of salt in tank 2, which makes sense because tank 1 is initially at 4 pounds, which is much higher than the amount of salt in tank 2. So it makes sense that tank 2 will increase up to a point until the dilution in tank 1 becomes significant enough to begin to pull down the concentration in tank 2, right? But then we can see that as we keep diluting tank 1, the concentration in tank 1 stays below the concentration in tank 2. Right. So imagine that this profile was the oxygen levels in the blood, monitoring the exchange of blood between the lungs and the heart. Right. And let's say you had this kind of profile for, let's say, a 30-minute window for a healthy individual. Right. You can use this as a benchmark to diagnose disease by comparing this to the profile in a patient who may be having, some cardiovascular issues or problems with their lungs. And you can say that, oh, I expect some kind of peak, after say 5 minutes. And if I'm not seeing that peak, then there could be something wrong, or anything of this sort. So having a superimposition of the two solution profiles is very important. We could also have decided to look at a more long-term behavior by plotting, let's say, a phase plane portrait of the same problem. So I'm going to attempt to do that. All right, so looking at the phase plane portrait, right? At this point here is my initial condition. Notice that tank 1 is at 4 pounds, tank 2 is at 2 pounds. So the curve starts from here, and then it traverses over time, along this curve here, right? So there's an initial increase, right, in the concentration, while tank 1 is decreasing, tank 2 is increasing, right? And then eventually both concentrations will fall to 0. Right? So here we are seeing the long-term behavior of both the salt concentration in both tanks going to 0. This is within an hour, right? This is within an hour. And so this is the power of the phase plane portrait, and then also the superposition. They can give you two sets of information about whatever is going on. Okay, so this is great. And we have just, solved, a very practical problem by using systems of equations. Okay. So this is the good news. The good news is that you can go from a higher order equation, for a system of equations to a higher order equation, and then use all the techniques that we've studied so far to solve this higher order equation. The only problem with this is when the system becomes large. Okay, so this is quite tractable for, like I said, a 2x2, two unknown functions, 3 unknown functions, maybe even 4 unknown functions. You can, wrap your head around this. But once you begin to get, in the realm of tens of unknowns, right, doing this becomes quite unwieldy, and we want to look at something more realistic. Okay, a more realistic approach, a more practical approach that is going to be more or less, the pain is going to be more or less independent of the dimension of the system. Okay, so let's look at to do that, we're going to think about systems of equations in matrix notation, right? And you know that once we begin to think of systems of equations as matrices, this allows us to handle much larger systems. Okay, so this is the motivation, and this is the background to being able to handle systems of equations more generally. All right. Okay, so let us assume that we have two equations. Right, so we have linear equations. This only applies to linear equations. So x prime is some a of t x plus some b of t y, and y prime is some c of t x plus d of t y. Okay. Now I can conveniently rewrite this as x prime y prime equals a of t, b of t, c of t, and d of t times x, y. Right? And if I set x bar to be x, y, then of course the derivative of x bar will be x bar prime will be x prime y prime. And so I can write this whole system as x bar prime is sum p of t times x bar. Right? And this is my system of linear equations in matrix form. And this is going to be the basis for the general methodology that we are going to introduce. Okay, so this doesn't matter if we have 10 unknown functions, right? We can still set up this matrix equation. Okay, now the method that we're going to discuss is peculiar to homogeneous systems. There's an extension to non-homogeneous systems, but we will not be discussing that. This is homogeneous, right? And you can see, wait, this is, yes, is it homogeneous? Yes, so this is homogeneous because in the first equation, we are dealing with x prime, right? And for x prime, we have x and y, and all of, so of course, every term here involves, the unknown function, both unknown functions, right? So unknown functions are x and y, and every term in the first equation involves the unknown functions. Every term in the second equation involves the unknown functions, right? If we had an extra, say, e of t and an extra f of t here, then this will be a non-homogeneous system, right? But at the moment, this is homogeneous because every term involves the unknown function or its derivative. Okay. So once we have a homogeneous system, we can put it in matrix form in this way. Okay, and what we're trying to get at is how do we write down the general solution to a system of equations? Okay, so if you think back to when we started talking about second order differential equations, right? We were able to write down the general solution by thinking about the general solution as a vector space, right? And we said that the general solution is for a system of a second order equation is a two-dimensional vector space, and so we needed two linearly independent vectors, which were solutions, to be able to write down the general solution. Right? Well, we're trying to do the same thing here. Okay, and the foundation for classifying the general solution in that case, when we had the second order equation as a vector space, was the fact that the principle of superposition held for a second order homogeneous differential equation, right? And so the question is, does the principle of superposition hold for a first order homogeneous system of differential equations? Because if it holds, then there is a promise of being able to impose the vector space structure onto this system of equations. Okay. Now the good news is the principle of superposition holds. Okay. And we can prove it. We can just take a very simple system of two unknowns, right? So let's say let x1 bar and x2 bar, let this be two solutions of the homogeneous system. X bar prime is p of t times x bar, right? Now, if these are both solutions, then it means that x bar prime 1, subscript 1, is p of t, x bar 1. And of course, just for the notation to be clear, x bar 1 is x11, x12. Right? And then x bar 2 is x21, x22. Right? So each of these solutions is actually a vector. Okay, just keep that in mind. A vector of two solutions has two solution components. Right. So this is true for x1. The same thing is true for x bar 2. right? So if x1 bar and x2 bar are solutions, then the question is z bar, which is the sum of x1 and x2, is that also a solution? Right? So we want to see if the space or the collection of solutions to the homogeneous problem is closed under addition, right? And then we'll verify that it's closed under scalar multiplication, right? And then that basically gives birth to the vector space structure. Okay. All right. So let's see. What is z bar prime? Right. We know that z bar prime is going to be x bar prime, x1 bar prime, plus x2 bar prime, because it's just a sum. Well, what is x1 bar prime? This is p of t, x bar 1, plus p of t, x bar 2. We can factor out a p of t. This gives me x bar 1 plus x bar 2. And I know that x bar 1 plus x bar 2 is z. So I have p of t z bar. And so I have the results that z bar prime is p of t z bar. And that is saying that z bar satisfies the homogeneous system of equations. Okay, and so this concludes the fact that, well, a sum of solutions to the homogeneous first order system is a solution. Okay, now what if I consider a scalar multiple? Okay, so let z bar be a times x bar 1. Then z bar prime is just a times x bar 1 prime, which is a p of t x bar 1, which is p of t a x bar 1. Right? And this is p of t z bar. Okay, so again, we verify that the scalar multiplication is closed, right? And so that implies that the principle of superposition holds for first order systems. And so we can generalize this for n solutions, right? To say that if we have n solutions of the homogeneous first order system, then we know that a scalar multiple or a linear combination of these n solutions will also be a solution of the homogeneous system. Okay. And so by virtue of the fact that the principle of superposition holds, we can impose and we can verify the other properties of the vector space. But based on this foundation, we can infer that the solution set for the homogeneous system is a vector space. Okay, and the same ideas hold if we have a system of two equations, then the solution space is a two-dimensional vector space. If we have a system of three equations, the solution space is a three-dimensional vector space, right? And what does that mean? It means that to be able to represent, if it's a two-dimensional vector space, to be able to represent any element of the solution set, we need two linearly independent vectors, right? If it's a three-dimensional vector space, we need three linearly independent vectors to be able to write down any solution of the homogeneous system, right? And that is how we describe the general solution. Okay, because being able to represent any solution of the linear system is the representation of the general solution, right? And so we need to think about, well, what does it mean for solution vectors in this context to be linearly independent? Okay, well, the definition is still the same, right? Now the elements of our vector space are themselves like, tuples, right? So they are n tuples. And so each x bar 1 here is really x11, x12, x13, x1n. So it's a vector, right? So if we have a whole bunch of these guys, which are solutions, xn1, xn2, xn3, xnn, this just doesn't have to be the same. It's the same, right? What do we mean by this collection is linearly independent? Why? Well, we think of each one as just a vector, right? And then the definition still holds. If we have a linear combination of these vectors that is trivial, right, then we must have that the coefficients have to all be 0. That's the only time when we're going to have a trivial combination. Okay, and this is the same definition we used, when we're dealing with just scalar vectors. Right? It's the same idea. Okay. So now that we have a definition for linear independence, we can identify, when we have, a linearly independent set of vectors, and by virtue of the fact that, if you have a system of n equations and unknowns, you have an n-dimensional vector space, we can write down the general solution, right? And we can say that, well, then, if you have n equations and n unknown functions, for the linear homogeneous system, then your general solution will just be a linear combination of n linearly independent solutions, right? And so our job is to figure out these n linearly independent solutions, and then we can write down the general solution. Okay, so just to show you that this idea of taking a linear combination of n linearly independent solutions, write down the general solution, is really not a foreign idea. Let's go back to example 3. Right, in example 3, we had the general solution to be x of t is c1 cosine of t plus c2 sine of t. And then we had y of t to be c1 over 2 sine of t minus c2 over 2 cosine of t. All right. Now, if I denote x bar as x of t, y of t, right, then notice that I can rewrite this equation as xy is c1 times cosine of t 1/2 sine of t, right, plus c2 into sine of t minus 1/2 cosine of t, right? And so notice that my x bar is really a linear combination of two vectors. Vector 1 being, let me call this u1. Well, let me just use the same notation. Vector 1 being x bar 1, and this being x bar 2. Right, I can write down my general solution x bar as c1 x bar 1 plus c2 x bar 2. Right. So this is not any different from the solutions that we've constructed so far. In that case, we thought of the general solution as a pair of functions, right? But in this case, we are thinking of the general solution as a vector at one point, just at one goal, and we are writing it as a linear combination of two vectors. But at the end of the day, it's the same representation. It's just a different point of view. Okay. And so, of course, the assumption here is that x bar 1 and x bar 2 are linearly independent. Right? In other words, this vector and that vector are linearly independent, because that's the only way the linear combination will generate a general solution. Okay. So how do we check to make sure that two vectors are linearly independent? All right. The check is no different from how we've checked linear independence so far. we're going to use a Wronskian. All right. And so the Wronskian is going to be defined slightly differently. If we have, let's just use 3 vectors to illustrate, or let's just use 2 vectors to illustrate. So if x bar 1 is x11, x12, and x bar 2 is x21, x22, we'll define the Wronskian of x bar 1 and x bar 2 to be the determinant of the matrix formed by first column as x1, x bar 1, so we have x11, x12, and then my second column will be x bar 2, which will be x21, x22. Right. And so the determinant of this gives us a Wronskian. Okay, and just like we defined below, we defined previously, the vectors will be considered linearly independent if the Wronskian is non-zero for each value of the independent variable, and the vectors will be considered linearly dependent if the Wronskian vanishes at each point, or for each, for each value of the independent variable t in this case. Right, and so we can immediately check if vectors are linearly independent. We have x bar 1 being cosine of t, 1/2 sine of t, and x bar 2 being sine of t minus 1/2 cosine of t. We can find the Wronskian. This will be the determinant of cosine of t, 1/2 sine of t, and we have sine of t minus 1/2 cosine of t. Right. Determinant gives us minus 1/2 cosine squared t minus 1/2 sine squared t, which is minus 1/2, which is clearly not 0. And so we know that these 2 vectors are linearly independent. And the expression we wrote down previously is actually independent, the general solution. Okay. And so going forward, our new task is to identify linearly independent vectors of the homogeneous first order system. Right. In the next lecture, we're going to come up with a technique for obtaining these linearly independent vectors. And once we find them, then we just take a linear combination to have the general solution. Right. So that's going to be the focus of the next lecture. And that is our final lecture for the semester. Right. So before then, try your hands at these practice problems just to get comfortable with the conversion idea, going from higher order to system to higher order. Look at some application problems with a mixture case, and then review the theory of superposition and how to actually use a Wronskian to check if vectors are linearly independent, and so on and so forth. Right. And so we'll take it from here in the next lecture and come up with a technique to find a set of linearly independent vectors to write down the general solution. And then we'll, find particular solutions, and that will be it. Okay. All right, guys, I'll see you next time for my final lecture. Take care.